Hello everyone. So far we have talked about convergences of sequence of random variables. Today we'll be talking about convergence of sequences of expectations of those random variables. Okay. So let me start with monotone convergence theorem. It's one of the simplest theorems. As the name suggests, it would deal with monotone sequences. Correct? So let me write down the statement, then we'll discuss its implications. Suppose xn is a non-decreasing sequence. So xn is a non-decreasing sequence of non-negative random variables. Okay. Defined on probability space omega fp. If it's already non-decreasing, so we know it's increasing. So if it is converging, so if xn converges to x on omega, so when I say on omega, I mean on entire omega, so it's pointwise convergence. Then expected xn increases to expected x. Okay. So a couple of things. As I said, first of all, it's pointwise convergence. Okay. Entire omega, it holds on entire omega, so it's a pointwise convergence. And we know expectations are monotone. So if xn's are non-decreasing, the sequence of their expectations would also be non-decreasing. Correct? x1 is less than equal to x2, less than equal to x3. That is what we have. And because expectation is monotone, it would be expected x1 would be less than or equal to expected x2, less than or equal to expected x3, and so on. So expected xn would also be a non-decreasing sequence, but of course it's a real sequence. Expectation is not random variable, and it converges, and it actually converges to expectation of x. It doesn't converge to any arbitrary number. Okay. So is it expected? So in general, if I want to write, this is same as saying that we can interchange limit and expectation if the sequence is of non-negative random variables. So what we know is limit xn equal to x, and now we are saying that limit of expected xn would be expected x, which is nothing but expectation of limit xn, because x is limit of xn. So we are saying limit and expectation can be interchanged. Okay. So this is monotone convergence theorem. Now some of you might have felt that this is actually quite restrictive. I mean, we are saying that the sequence should be of non-negative random variables and it should be non-decreasing. So even though the statement says monotone, we are not allowing for decreasing sequences. Okay. However, there are certain corollaries which could be useful for such other subcases. So let me state one such result. So first of all, we'll talk about relaxing the assumption of non-negativity. Okay. So suppose y is less than or equal to xn and xn increases to x. Okay. On omega, and y is an integrable random variable. Okay, so I am not saying xn's are non-negative. Now xn's can be negative also. The only condition that I am putting is xn's should be bounded below by some integrable random variable. Do you remember integrable? The expectation should be finite. Okay. Then expected y is less than or equal to expected xn. This is okay because this happens by monotonicity, and expected xn converges to expected x. Okay. So we are trying to relax non-negativity here. So we don't need xn's to be non-negative. However, we can't relax it completely. We need at least some lower bound. Can you think of a proof? It's pretty easy. Because we know the result for non-negative random variables, let me define Zn as xn minus y. Okay. Since y is anyway free from n, Zn would converge to x minus y. Correct? Because xn would converge to x, y anyway remains constant. Zn would converge to x minus y. Again pointwise. Pointwise convergence has all the properties of convergence of sequence of real numbers, because for every omega it is nothing but a sequence of real numbers. Okay. And now, since xn is greater than or equal to y for every n, Zn will always be non-negative. And can I also say that Zn is an increasing sequence? So xn, we know xn is increasing means xn is less than or equal to xn plus 1. So xn minus y is less than or equal to xn plus 1 minus y. Correct? We can subtract y from both the sides. So Zn is less than or equal to Zn plus 1, because that is my definition of Zn. Okay. Hence, I now have Zn as a sequence of, as a non-decreasing sequence of non-negative random variables, and that's what we need. So Zn, expected Zn would converge to expected Z. We can say increases to. Z is the limiting random variable, and what is Z? X minus y. So now I have expectation of xn minus y converges to expectation of x minus y. And we know expectation is linear, so expected xn minus expected y converges to expected x minus expected y. I can split expectation. So I can add expected y to both the sides. Again, it's a sequence of real numbers. Now that it's in expectation, it's a sequence of real numbers. So I can add expected y to both the sides, and I get expected xn converges to expected x. Okay. So the things are now generalized slightly. We don't need non-negative random variables. We just need a sequence of random variables which is non-decreasing, and it has a lower bound in the form of an integrable random variable. Okay. So this is one relaxation of the assumption. Let us go to the second relaxation. So why do I need non-negative? Can I extend it to say negative? Or can I make it decreasing sequence? So yes, that is possible slightly. So suppose xn's are all negative, so 0 is greater than them. So 0 is greater than or equal to xn's, and xn decreased to x now. So I am reversing two things. Originally the sequence was non-decreasing, now I am making it non-increasing. Correct? And originally the random variables were non-negative, now I am making them non-positive. Okay. So this happens on omega. Then, so this is second corollary. Then expectation of xn decreases to expected x. Okay. Now I think you can surely think about the proof. What I'll do is, what I know is xn's are less than or equal to 0. So minus xn's would be greater than or equal to 0. Further, xn is less than or equal to xn minus 1 now, because they are decreasing. So minus xn would be greater than or equal to minus xn minus 1. So minus xn sequence would be increasing, and it is a sequence of non-negative random variables. So I can apply the monotone convergence theorem to this sequence, and I will say expectation of minus xn increases to expectation of minus x, which is same as saying minus expected xn increases to minus expected x. Therefore, expected xn decreases to expected x. Just multiplying by minus sign, so the order gets reversed and the convergence is still valid. Okay. So from the same result, we got some result at least for decreasing sequences, and of course non-positive sequences. Okay. Some application of this result we'll see now. So suppose xn is a sequence of non-negative random variables. Okay, xn is a sequence of non-negative random variables. Then expectation of summation xn n greater than or equal to 1 is same as summation expected xn. Now some of you might be thinking, why do we need this? We always do this. No, we don't always do this. What we do is, we take expectation inside sum, agreed, but it is always a finite sum, whereas this is an infinite sum. I am just saying n greater than or equal to 1, so n can go till infinity. Okay, so this is an infinite sum. So in general, for infinite sum, we don't know whether expectation can be taken inside the sum. However, here we are claiming that that can be done, and we are going to use the results that we proved just now or discussed just now. Okay, so let me define Zn as sum over xi, I going from 1 to n. So this is like, this summation xn is a series. So this is like partial sum of that series from real analysis, if you can recall. Okay, so Zn is summation xi, and this is a finite sum, so I can say expectation of Zn is summation expected xi, because this is now finite sum, I going from 1 to n. Okay, and what we have is now, because xn's are positive, xn's are non-negative, my Zn's are also going to be non-negative. Further, Zn plus 1 is Zn plus xn plus 1, correct? By definition, because Zn is sum up to n, and now I want sum up to n plus 1, so I just have to add xn plus 1. And because xn plus 1 is non-negative, this is always greater than or equal to Zn. So the sequence Zn is non-decreasing also. Therefore, expected Zn converges to the limit expected Z. Okay, and expected Zn is this. So summation expected xi, I going from 1 to n, converges to summation expected. Okay, it converges to expectation of sum over xi, I greater than or equal to 1, because that is Z, entire infinite sum. Okay, is it okay? And this is nothing but, convergence of series for this. Okay, so this series converges, but where would this series converge in general? Because this is a series, in general this series would converge to its own infinite sum, means this should converge to sum over expected xi, I greater than or equal to 1. Ideally, because this is a series of expected xi. So we are claiming that these two are equal, because a series cannot converge to two different limits. Hence what we have is sum over expected xi is same as expectation of sum of xi, because the current monotone convergence theorem told me that it converges to this limit, whereas my series knowledge tells me that it converges to this limit. So both the limits must be same, and hence we have proved that the expectation and infinite sum can also be interchanged, provided that all the random variables involved are non-negative. Okay, so these were some applications of monotone convergence theorem. Now let me go to another important result, which is known as Fato's lemma. Okay, so Fato's lemma. So let me again write down the statement first. Suppose xn n greater than or equal to 1 is a sequence of random variables defined on omega f p. Fato's lemma actually consists of three parts. So first part says, if y is an integrable random variable such that y is less than or equal to xn, then expectation of lim inf xn is less than or equal to lim inf of expected xn. Okay, So if y is an integrable random variable and y is a lower bound for xn, then expectation of liminf is less than or equal to liminf of expectation. This is one part of Fato's lemma. Second part says if z is an integrable random variable such that xn is less than or equal to z, then lim_sup expected xn would be less than or equal to expectation of lim_sup xn. Okay, so what we are saying now, z is an upper bound for xn's, then lim_sup has this relation, and now as a consequence of these two we have third result which is important. So if y and z are integrable random variables such that xn's are bound between y and z, okay, and if xn converges to x almost surely, then limit expected xn is expected x. Okay, limit of expected xn is expected x. Now see, we won't go into the proof of first two parts, and third part also we won't exactly prove rigorously, but let me give you an idea why that would work. So what the first two parts are saying is this liminf and expectation would have some relationship. So in the third part we have both the conditions in first two parts, right? We have y and z, two integrable random variables, y is a lower bound, z is an upper bound. So both the things that are true in first and second would hold. So I would have expectation of liminf xn less than or equal to liminf expected xn, and because in general for any sequence liminf is less than or equal to lim_sup, I can write this is less than or equal to lim_sup expected xn, and because of the second part I have this further less than or equal to expectation of lim_sup xn. Correct? See now, here we are using usual relationship liminf less than lim_sup, and this part comes from part 1, this part comes from part 2. But now we are also saying that xn converges to x. Okay, so liminf xn and lim_sup xn would actually be same. It would be the limit x whatever it is. Okay, ideally it would happen only if the convergence is pointwise. We'll deal with it a bit later. So now I have expected x on first as the first term of this inequality, expected x as the last term of this inequality. So in between two things must also be expected x, because then only the inequality would hold, right? Lowest among them is expected x, highest among them is expected x. So the intermediate things also have to be expected x. So what we are getting is liminf of expected xn and lim_sup of expected xn both are same, and they are same as expected x, and that is what exactly we are saying. Both are same means limit exists and it is same as expected x. Okay. And now about the pointwise almost sure business. As I said, ideally this would hold only if the convergence is pointwise. However, when we go from pointwise to almost sure, we leave out only those omegas which have probability 0. And we know in expectation those points don't contribute. Those which have probability 0, they don't contribute, right? So because expectation is integral of x into probability, so if probability is 0, that part won't be there. Hence it works only if the convergence is just almost sure and not pointwise. Okay. Now as a consequence of this we have another important corollary. So let me write that. So we just said that we need to have two bounds, one lower bound and one upper bound. So can I have some kind of common bound? So let us do that. So this is now a corollary to Fato's lemma. So suppose xn is a sequence of random variables defined on again omega fp, and now if y is an integrable random variable, such that mod xn is less than or equal to y and xn converges to x almost surely, then expected xn converges to expected x. So Fato's lemma says that yes, you need almost sure convergence and you need an integrable random variable which provides lower bound and another integrable random variable which provides upper bound. What I know right now is mod xn is less than or equal to y, but we all know this means minus y is less than or equal to minus y is less than or equal to xn is less than or equal to y. Okay, so now xn is bounded below by a certain random variable, bounded above by another random variable, and because y is integrable, minus y is also integrable. Expectation of y is finite means minus of expected y is also finite, and hence we can directly apply third part of Fato's lemma and the result is true. Okay, so this is an interesting result. But of course, you might again be thinking almost sure convergence is again a slightly strong assumption. So can we do something for a weaker convergence, something like say probability convergence? So that's where Lebesgue dominated convergence theorem is going to help us. Okay, so Lebesgue dominated convergence theorem. So suppose xn is a sequence of random variables defined on omega fp, and y is an integrable random variable such that mod xn is less than or equal to y. Almost surely. Now we don't even need pointwise, we need almost surely. So if xn converges to x in probability, then expected xn converges to expected x. So now two things. First, we are saying that the bound should be almost sure, means we don't need bound on every omega. It is enough to have bound on those omegas which have non-zero probability. So those omegas which have zero probability, we don't care about their values, because again in expectation that's not going to contribute. And now we have a weaker condition. So in the Fato's lemma and the earlier result we needed almost sure convergence. Now we are saying that even if xn converges to x in probability, it is enough. Still we can have convergence of expectation sequence. Okay. So that way now Lebesgue dominated convergence theorem is giving me something extra. Okay. So this is again one of the important results. Okay. So let me stop here. Thank you.